Hello, my name is Katie Antilla, and I'm a fifth-year PhD student in chemical engineering at Stanford. I grew up in Los Angeles, California, and went to Caltech for undergrad, where I studied chemical engineering with a focus on biomolecular engineering. I'm now doing research in the lab of Professor Shan Wang in material science and engineering, where I work on developing in vitro diagnostics for cancer applications. And I'll be presenting a poster titled Magnetoresistive Biosensor Assay for Detecting Circulating Tumor DNA in Non-Small Cell Lung Cancer. Lung cancer is a serious problem today. It's currently the leading cause of cancer death worldwide, and about 80% of those cases are non-small cell lung cancer, or NSCLC. One way people are working to improve lung cancer outcomes is by replacing or augmenting existing treatment methods like surgery, chemo, and radiation therapy with targeted drugs, which can have significantly fewer adverse side effects. The effectiveness of these targeted drugs relies on the presence of specific mutations in the tumor, which can change over time. Currently, the main way to detect and monitor these mutations in the clinic is by going into the lung and taking tissue biopsies, which are obviously very invasive. The other major ways that lung cancers are assessed and monitored rely on imaging technologies like X-rays and CT scans, which are very expensive. One promising new alternative to tissue biopsies and imaging tests is the use of liquid biopsies, which test blood, urine, or other bodily fluids to assess patient tumors in a less invasive and less expensive manner. There are a lot of different cells and biomolecules present in the blood, but in our case, we're focusing on circulating tumor DNA, or ctDNA, which is released by tumor cells into the bloodstream through a variety of mechanisms. By testing for ctDNA, we can detect mutations and monitor tumors with a simple blood draw, allowing for less invasive and less expensive testing. However, since ctDNA is often only present in very small quantities in the blood, we need a technology sensitive enough to accurately detect it. Our lab's giant magnetoresistive, or GMR biosensor technology is well suited for this application because of its high sensitivity, multiplexing capabilities, and low cost, along with its ability to be incorporated into future point-of-care devices. The sensors are arrayed in an 8x10 grid on a small printed circuit board. The general concept behind our technology is that the GMR sensor can detect a signal from the presence of magnetic nanoparticles, but only when they're in close enough proximity to the sensor surface, which happens when two DNA strands hybridize together and tether the nanoparticle to the surface. The strength of these DNA strands' hybridization depends on how complementary their sequences are, and thus can be affected by the presence of specific mutations in the DNA sequence. So, the goal of my project is to use these GMR biosensors to develop an assay that can detect target mutations in ctDNA, which can ultimately be used for less invasive lung cancer treatment selection and monitoring. In particular, we first developed an assay targeting 3 clinically actionable mutations in the EGFR gene, and we're now working on developing an assay targeting 6 mutations in the KRAS gene. If you're interested in learning more about this project and the results we've gotten so far, come check out my poster.